In this problem, we have this table, and the instructions say complete the following table for refrigerant 134A. So basically, we have refrigerant 134A, and we have some different data given. So we have some temperatures given, we have some pressures given, some specific volumes, and phase description. And what we want to do is take the data that we're given and determine the data that's missing or that we weren't given. So for instance, on this first line, and I'm just going to call these lines A, B, C, and D. So on the first line, we were given that our refrigerant 134A has a temperature of -4, and it's at 320 kilopascals, and we want to figure out what the specific volume is and what the what phase it is. So is it a mixture? Is it a compressed liquid? Is it a superheated vapor? And so the way we're going to solve these is you can calculate the temperature, pressure, and specific volume using an equation of state, although the equation of states and the math required can get pretty complicated depending on what your temperature and pressure is and depending on what your substance is. So a lot of this data is tabulated in tables. And so what we can do is we can look up this information on a table. So let's start with this first one. So we have, so I'm going to just start here. So A is the first row. So our refrigerant 134A is at -4 degrees Celsius. And so what we need to do, and the pressure is 320 kilopascals. So what we need to do is we want to look this up on a table. Like we want to look up the specific volume on a table from this temperature and pressure. So we need to know, so thermodynamic tables are divided into a saturated liquid vapor mixture table, compressed liquid table, and superheated vapor table. So we need to determine if this is a saturated mixture, compressed liquid, or superheated vapor before we can look up what the specific volume is. So the way we're going to do that is we're going to go look at the table and we're going to see what the saturation pressure is at -4 degrees Celsius. And we could also do this the other way around. We could look up the saturation temperature at 320 kilopascals. And so let's go do that. I'm going to go to the tables. So here's our table for saturated refrigerant 134A. And I'm looking at the temperature table. So I have -4 degrees Celsius. So what I'm going to do, so this is, so if we look right here, look at this table, we have, I have the saturated, so I'm looking at, I'll erase that. So I'm looking at the saturated refrigerant 134A, and I'm looking at the temperature table right now. And so what I want to do, I was given that the temperature is -4 degrees Celsius. So I'm going to look at this temperature column, and I'm going to go to where it says -4 degrees Celsius, and I'm going to get the saturation pressure. So at -4 degrees Celsius, the saturation pressure is 252.85 kilopascals. And like I said, we could also look this up at the pressure given. So I'm going to show you how to do that real quick. So what I'm going to do, this is the temperature table, so I'm going to go to the pressure table. So here's the refrigerant 134A pressure table. So this is so it says saturated refrigerant 134A pressure table. And then notice how this first column is now pressure. So now we can look up the saturation temperature at the pressure given. The pressure given was 320 kilopascals, so I'm going to look here. And at 320 kilopascals, the saturation temperature is 2.46 degrees Celsius. All right, so let's go back to the slide. So we just looked this up on the table. At negative 4 degrees C, Psat is equal to 252.85 kilopascals. And we also looked up the saturation temperature. So at 320 kilopascals, Tsat is equal to 2.46 degrees Celsius. Really, we only needed one of these to determine our phase, what phase we're in, but I looked up both just to show you that you can look up both. So if we look at our given pressure, first of all, the pressure, so 320 kilopascals, is greater than Psat. So 320 kilopascals is greater than Psat at that temperature, because Psat is this 252.85 kilopascals at minus 4 degrees Celsius. Because the pressure is greater than the saturation pressure, that means that we have a compressed liquid. We could have also determined this from this temperature. So the temperature given, so minus 4 degrees Celsius, is less than Tsat, which is 2.46 degrees Celsius. So since the temperature is less than the saturation temperature, this would also tell us that we have a compressed liquid. So I'm going to put that we have a compressed liquid in the phase description. So now we know what table we need to look at to determine what the specific volume is. Since we have a compressed liquid, we would normally look at if a compressed liquid table were available, we would get that information off the compressed liquid table. It turns out for a lot of substances, the compressed liquid data is lacking, and when you don't have a table for the compressed liquid, you're going to assume that it's a saturated liquid, so then you can look at the saturated table for whatever it is you're looking at, so in this case refrigerant 134A, and you're going to look at the temperature. So what we're going to look up is VF, so the specific volume of the saturated liquid at minus 4 degrees Celsius. And so let's go back to this table. Since we want to look it up by temperature, we're going to go to the saturated refrigerant 134A temperature table. So if we go to minus 4, which is right here, and then go over, we're looking for the saturated liquid, which that's this column. So if we go over, then that means that the specific volume is 0.0007644 meters cubed per kilogram. All right, so we just looked up that the specific volume at negative 4 degrees Celsius was 0.0007644 meters cubed per kilogram. So I'm going to put that right here. So 0.0007644 meters cubed per kilogram. And remember, we looked this up on the saturated liquid, or we looked up the specific volume for the saturated liquid on the saturation table, because there isn't, or at least in the book I'm using, which is Thermodynamics and Engineering Approach, there's not a table for the compressed liquid for refrigerant 134A. So So if you don't have a table available for compressed liquid, you're just going to assume that it's a saturated liquid, and you're going to look it up at the temperature given. So you want to make sure you look it up at the temperature given and not the pressure given. All right, so now let's do B. So for B, we still have refrigerant 134A, and it says that it's at 10 degrees Celsius, so 10 degrees Celsius. And it gives us the specific volume. So what we need to do is we need to look up the specific volume for saturated liquid and saturated vapor at 10 degrees Celsius so we can determine what our phase is, because we need to, in order to look up the pressure, we need to determine if we have a compressed liquid, a saturated mixture, or a superheated vapor. So let's go back to our table. All right, so I'm looking at, so I need to look up I need to look up the specific volume of the liquid and the vapor at 10 degrees Celsius for refrigerant 134A. So I'm still on the same table I was using before, only now I'm going to go down to the 10 degrees Celsius, and the specific volume of the liquid is this, so 0.0007929 meters cubed per kilogram, and the specific volume of the vapor is 0.049466 meters cubed per kilogram. So let's just write these down real quick. So VF is 0.0007929 meters cubed per kilogram. And the specific volume of the vapor is 0.049466 meters cubed per kilogram. Just to remind you, the specific volume that we were given was 0.0065 meters cubed per kilogram. What this means is that the specific volume of our refrigerant is less than the specific volume of vapor. So 0.0065. So the specific volume given is 0.0065. So this means that our specific volume is less than the specific volume of vapor at that temperature, and the specific volume is greater than the specific volume of the liquid. So this means that we have a saturated mixture. So that means that since we have a saturated mixture, that means that the pressure is the saturation pressure. So at 10 degrees Celsius, so we're right here again, 10 degrees Celsius, let's just scroll up a little bit. We want to get the saturation pressure. At 10 degrees Celsius, the saturation pressure is 14.89 kilopascals. So that means that at 10 degrees Celsius, P sat is equal to P sat is equal to 414.89 kilopascals. So for B, we determined that, well, let's just write this down again. So at 10 degrees Celsius, the specific volume of a saturated liquid is 0.0007929, and the specific volume of the saturated vapor is 0.049466. The specific volume that we were given right here is 0.0065, so that means that our specific volume is less than the specific volume of the vapor and greater than the specific volume of the liquid. So this meant that we had a saturated mixture. So I'm going to fill that in here. So we have a saturated mixture. So this means that we have a mixture of liquid and vapor. And since we have a saturated mixture, that means that our pressure is P sat at the temperature given. So remember, we looked that up on the table. So at 10 degrees C, Psat is equal to 414.89 kilopascals. So let's write that here. So 414.89 kilopascals. Now let's look at C. So for C, we're given the phase, so we're told that it's a saturated vapor, and we're given the pressure as 850 kilopascals. Since it's a saturated vapor, we know what table we need to look at to get the temperature and the specific volume. So the temperature is going to be the saturation temperature at the pressure given, and the specific volume is going to be the specific volume of the saturated vapor at the pressure given. So let's go look at the table. This time we want to look at the table that's given in pressure because we're given a pressure. So I'm looking at the saturated refrigerant 134A pressure table, and I have a pressure of 850 kilopascals, and I have a saturated vapor. So let's go down here to 850 kilopascals. So at 850 kilopascals, Tsat is equal to 33.45 degrees Celsius. So 33.45 degrees Celsius. And then since we know we have a saturated vapor, we know the specific volume is the specific volume of the saturated vapor at this pressure and saturation temperature. So that's this. So Vg is equal to 0.024091 meters cubed per kilogram. So at 850 kilopascals, Tsat is 33.45 degrees Celsius, and the specific volume is 0.024091 meters cubed per kilogram. All right, now let's do this last one. So let's do D. So for D, we're told that we're given a temperature and pressure of the refrigerant 134A. So we're told that it's at 90 degrees Celsius and 600 kilopascals. So what I'm going to do is look up the saturation temperature at this pressure, so at the 600 kilopascals. So let's go to our table. Looking at the pressure table for saturated refrigerant 134A, and I want to look up 600 kilopascals. So at 600 kilopascals, Tsat is 21.55 degrees Celsius. And our given temperature is, so we were told that our temperature was 90 degrees Celsius. 90 degrees Celsius is greater than Tsat, so that means that we have a superheated vapor. So that means that since we have a superheated vapor, we need to look up our specific volume on the superheated vapor table. So let's go find our superheated vapor table for refrigerant 134A. So this is our superheated vapor table. Let's go back up here. So this is our superheated vapor table for refrigerant 134A. And I know what the temperature and pressure are. So the pressure is, so I'm going to look up the pressure. It's 600 kilopascals. The table is giving pressure in megapascals, so I need to convert that to megapascals. So 600 kilopascals is equal to 0.6 megapascals. So what I'm going to do is find the 0.6 megapascals, which is right here. And then I'm going to look up the temperature. So I'm given that the temperature is 90 degrees Celsius. So at 90 degrees Celsius, here's a specific volume. The specific volume is 0.46318 meters cubed per kilogram. All right, so I'm working on this last one. So I determined that when the refrigerant 134A is at 90 degrees and 600 kilopascals, this is a superheated vapor. So I'm going to fill this in. And the specific volume, which I got off the superheated vapor table, is 0.046318 meters cubed per kilogram.